I'm still living not far from here. I'm driving down there through the day. Not yet. Good cause.
Creeping along, but I'll try to get my.
I still live right there where I want to work. But yeah, like 45 minutes to drive down there, and probably cut down like a few times, find a few so look at but slowly there.
Hi everyone that's joined us online. I'm Dave and I'm going to be streaming today. So that's that. Okay. Everyone's.
Are things here?
If you're watching online, folks are just getting here, especially the committee. If there are problems with the stream or you want to ask a question in the Q&A part, just type it into the comments window and I'll relay it, or maybe somebody else that's monitoring it will relay it on your behalf. Also, if you see a problem with the stream, like video or audio or something, and you can't hear, then you can type something there too, and I'll be aware of it. Thanks a lot.
Hey, how's it going? Good to see you.
Hey, Julius, hi.
Hey, Dave. Hey. Okay, so Jonathan's almost here. He said he's in sight of CCRMA.
Okay.
So, so yeah.
So he could be in a plane over.
Yeah.
Or a helicopter.
Tom Rausch from Berlin says hi. He says go Kurt. You know somebody? Well, Tom Rausch. You know who that is? Is that somebody who's? No. Oh, well, hey Tom.
Workers. Oh, could be Max. Max never uses.
Yeah, maybe somebody's tuning in. Yeah. Oh, Robert Hamilton. He says yay Kurt. Okay. Let me just. Yeah. Do you want to wave back at folks? You're taking a wave.
Wave back.
Yeah, Kurt, do you want to wave real quick? Yeah.
Rob, hey. Yeah, right.
Yeah. Indented in the images on them, so they look like they're 3D.
Projection mapping.
Yeah, but it's on this indented. It's like the reverse of sculpture. It's and they're able to get something like they're looking at
Everybody who's scheduled.
and use their avatar projected on their.
Yeah, my class is,
Or your image.
stopped at the computer. Problems are and how they, and what the problem is and needs to be solved.
Oh yeah, no,
It's pretty smooth. I don't know what percentage of it they try to post with. Friction's really nice. There's a lot of stuff.
good sweating, inflation.
Nice. Relaxation. You kind of have to solve the whole network before you know which way it's moving.
John Maple's here, he's just getting set up with the live stream in the other room, the projector using my keys. So Francois Johnson, it's like set up.
Aaron Martin says good luck.
We can go check, it's next door. Can I see your ID? Yeah, he doesn't like the lighting in here. He doesn't like lighting in most places. There's only like 2 restaurants I heard him have dinner with him. Wilfernino and Cafe 220. And he plays before sundown. Okay, he'll sit outside and in the hallway right here, you know, just leave the lights off. So plug out your office and pitch dark.
Well, I should get any of
What kind of music student is it lighting? Yes, lighting and I'm thinking about the I don't see it.
Okay, so it's
Yeah, well,
what, should I just go or you introduce me or?
Welcome to the thesis defense of Kurt Werner. Today is the day you will hear a story of victory in taming the wave digital filter for more general topologies in multiple nonlinearities in non-typical topologies like bridge circuits. And so without further ado, I don't want to take away from this already way too short time that you have. Kurt Werner.
Thanks for coming. So, in case you didn't read the abstract, which is long and wordy and has a lot of math terms, here's a clip from popular television series Futurama to explain the thesis to you.
Now I'll just have someone duplicate your guitar. That sucker! Her sound is unique. All your fancy technology will never be able to copy this guitar.
Using my fancy technology, I can make an exact copy of this guitar. We can take a unique and beautiful object and easily reduce it to a formula for mass production. I call the process science.
So we could basically end it there, but to go into a little bit more detail, this is the world we're living in. Musicians like vintage stuff. This includes old guitar amplifiers, old drum machines, old synthesizers, old fuzz boxes and distortion pedals, and all manner of analog electronics that they use to create or modify sound. All these things are made out of little circuit bits, triodes, resistors, capacitors, inductors, little wires, potentiometers, all these electronic things. So because these things are so great and they sound fun and people like to use them, but they're rare, expensive, fragile, and don't fit into a modern workflow, and heavy also, if you've ever tried to pick up the power amp stage from a tube amp. People in this field called virtual analog try to make mathematical models out of these things. So you can build that into a tiny little 1-ounce DSP chip that you can mass manufacture. You don't have to pay tens of thousands of dollars for some great vintage piece of gear. So within the field of virtual analog modeling, there's other applications of this also. You can take old instruments and extend what they're capable of doing. And you can use virtual analog modeling to design new instruments. Say you have an idea for how a new amp would work. Instead of building it dozens of times, tweaking things, you can make a simulation. Even if you know what parameters you want to, what parameters you can change, you could design some sort of objective function you want to maximize within some circuit topology, and let this thing have at it and try all the different possibilities for you until it does what you want. So there's a couple different applications of this besides just getting an awesome old sound. So two big classes of approaches to virtual analog modeling are black box modeling and white box modeling. In black box modeling, you don't really care how something works, you just care that it works. So you try to find some way to characterize the system, and then you make some new thing that just has the same result. And in white box modeling, you actually use knowledge of the system, in this case the physics of the electronic components, to build a model up piece by piece. And it's kind of the opposite. In that case, you know why it works, but not really what happens. For instance, if you had an amplifier and you know it sounds crunchy, black box modeling would involve trying to figure out what crunchiness is, and then making something else which is also crunchy. And white box modeling would involve making a little mathematical model of each resistor and capacitor, plugging them all together, never knowing what crunchiness was, but then listening to the result and deciding whether or not it is indeed crunchy. So we're going to be doing white box modeling. The two main flavors of that are state space and wave digital filters. And there's a lot of great work on state space out there in the literature. Mostly Martin Holters and David Ye and Rudolf Sulzer, and recently there's some work out of SARC by Martin van Wallstein and Ben Holmes. But the field we'll be working on is wave digital filters, which are these great things which have all this promise, but up until a couple of years ago didn't really work in general for most things you would care about. So just by way of introduction to the wave digital filter framework, this was a branch of electrical engineering started by Alfred Fettweis, a German guy in the late 1960s. And originally they just wanted to make digital filters. They didn't care about crunchy old analog audio circuits. In fact, most of the awesome crunchy old analog audio circuits hadn't been invented yet. So they just wanted to make digital filters from analog prototypes, which they already knew how to design, without having to think about digital things. So you could take an analog filter, use some step-by-step procedure to turn it into a digital filter, and just be done. It was a very mature field by 1986 when the granddaddy of all wave digital filter review articles came out, Wave Digital Filters Theory and Practice. And as far as we're concerned in music and audio, we started paying attention to them in 1987. That's the earliest reference I know about, when Julius wrote about their relationship to waveguide modeling, which you all know from class, but that's about modeling distributed systems of tubes and strings and those kind of things. And since then, people in the music technology field have used the wave digital filter approach to model mechanical systems like the tone holes in clarinets, piano hammers in flight, clarinet reeds, and other kind of mass spring oscillators and things. They've even been extended to the distributed case by Fettweis, but the book on wave digital filter models of distributed systems is written by Stefan Bilbao. Literally the book. It's an intense book, and we won't talk anymore about distributed systems, but that wave and scattering methods for numerical simulation, that's where it's at. After that, people started taking notice of how you could use this to do virtual analog modeling. And here at CCRMA, Julius and David Ye did some work on guitar bright switches and diode clippers, and showing how some of these simple audio circuits could be approached with the wave digital filter paradigm. Over in Europe, there's a lot of work on trying to figure out how to use wave digital filters to model triode amplifiers and distortion circuits, like from the Blues Breaker and the Tube Screamer by Ibanez, and even some rudimentary virtual analog oscillators. Augusto Sarti and Giovanni De Sanctis worked on a square and triangle wave generator. So up to this point, around 2010, there are all these great things that wave digital filters could handle. So they could handle circuits with one nonlinearity, so single diode or single transistor or single triode. They could handle multiple nonlinearities only in very specific topological cases. And then they could handle other things outside of this narrow range of circuits only with ad hoc simplifications. Basically, you had to get very smart and make simplifications and make these hacks and workarounds. But there was no systematic general procedure for making something out of a given circuit. They can also handle any number of series or parallel topological connections between electrical elements. Resistors and capacitors in parallel, in series, inductors in parallel with the series combination of a resistor and the parallel combination of a current source and the series combination of the series combination, and so on. And also two-port linear elements in feed-forward configuration. So if you had a transformer decoupling one part of the circuit from another part, that would be allowed. But if you had a transformer with some feedback around it, it would not be allowed. So with all these things that they can handle, they couldn't handle a lot of situations which are incredibly common, even to the point of being ubiquitous in audio circuits. So they can't handle multiple nonlinearities in general. They can't handle complicated topologies, which can't be decomposed into series and parallel connections. They can't handle op-amps unless they're in a very specific differential amplifier topology. And they can't handle the combination of these things. So in this dissertation, what I worked on is modeling any audio circuit using the wave digital filter framework. The problem that they can't handle topologies, linear elements, or multiple nonlinearities is solved by these two major contributions. One is derivation of a scattering matrix for the class of all circuits, which include complicated topologies and absorbed multiport linear elements, and a formulation of the wave digital filter root as a nonlinear state space system, which can be solved during the using the K method or a Newton solver. And this is applicable to circuits with any number of nonlinearities in any topology. And the result of all this is that given your favorite audio circuit, there's always a way to write out the wave digital filter system as a block diagram, and there's always a way to represent mathematically what's going on inside of each block, and there's always a way to connect those blocks together. So you're set, and then it works. The story that I'm going to tell in this talk is the story of the Roland TR-808 rhythm composer. It's a drum machine from 1980. It was manufactured for 3 years, a couple thousand, maybe 12,000 of them were made, and it's incredibly popular. So let's play a couple, let's play a couple clips of it. So that's Marvin Gaye, and that was actually one of the first uses of the 808 in pop music. Another example comes from Beastie Boys. So especially the Beastie Boys clip, you notice this like booming bass drum. And if you've heard any other rap music or pop music or EDM, you've probably heard that bass drum a lot. It's even used when it's cranked up so that it lasts a long time. It's used even as a bass line. It's utterly ubiquitous in popular music. It's been used more than any other drum machine, period.
Says Roland.
According to Roland's blog. I think techno people might argue that the Roland TR-909 is more important than the successor, but I would argue that you don't hear anybody rapping about the TR-909. So here's, if the thing doesn't look familiar to you and the name doesn't sound familiar and you're like, yeah, that sounds like a kick drum, but I don't really know it from any other kick drum, maybe you've heard some of these songs which make reference to the TR-808, just so by...
We got that 808, that boom 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 time. Make your heart beat like an 808 drum. It's my love, your drug. 808s and hammers and knocking. Just a snare in the 808. Hey, these are remedies, get the 808. Looking like a hot date, banging like an 808. 808.
Stop me, go hard like I got an 808 in my heartbeat. And I'm eating at the beat like it gave a little speed to a great white shark on shark week.
So all those times and many more when people are singing about the 808, this is what they're talking about. And that booming bass drum is one of the most well-known and important parts of the sound of the 808. So that will be the focus of this dissertation, or as the case study. We're going to break that thing into pieces, and we're going to show how to model each piece. Each of those 4 pieces isn't so easy to model, so we'll have to introduce some new wave digital filter theory to do so. We end up with something great that preserves that awesome kick drum sound. So this is the circuit, and it's got a couple controls. It's got a control for the level, it's got a control for the tone, and it's got a control for the decay. That's the difference between the sort of Marvin Gaye setting where it's just like doop doop, and the Beastie Boys setting where it's like doom and lasts for 2 seconds. So we'll break this into 4 parts. We have the output filter on its own, which we'll talk about in the first chapter. The bridge T resonator, which we'll talk about a simplified linear version of that in the second chapter. The pulse shaper, which takes the control signals off the chip and translates them into something that the resonator can work with. And then finally, in the last chapter, when we introduce all the full nonlinear stuff, we'll talk about the envelope generator and the full nonlinear version of bridge T resonator with all the diodes and transistors and the fun stuff added back in. So to start with, here's the wave digital filter concept in a nutshell. You take your favorite audio circuit. This is actually the basement tone stack. You break it into pieces. So you kind of look at what are the pieces that make it up, in this case resistors and capacitors, and then you write some code to implement each thing. So to zoom in a little bit more, we look at the circuit as a combination of the components and a network that connects them together. And for each little piece in that network, so each piece in this block diagram in the center, we have to figure out some sort of mathematical operation that will take inputs to that block and translate them into outputs. So what wave digital filters use is a scattering formalism. So you take your Kirchhoff domain representation, that's in terms of voltages and currents, that's usually how we think about electronic circuits. You do this variable change, which is identical to the traveling wave formulation from waveguides or wave anything, and you get to this other representation, which is parameterized by port resistance. And so what you then can do is tune the port resistance, which in this situation is only an arbitrary thing parameterizing the change of variables. You tune that to break the delay-free loops between blocks. So this, on the right there, you've got that signal flow graph. A comes in, gets multiplied by something, and B comes out. So if you had two of those things hooked together, you would have a problem. You wouldn't be able to derive some explicit sequence of calculations to solve for each node in that signal flow graph. And if you had hundreds or thousands of things hooked together, it'd be even more hopeless. So the wave digital filter formalism gives you a way to resolve those loops. In this case, you would pick R naught to be equal to R, and it would turn that multiplier into 0 and break the loop. So you also do a similar thing with multi-port elements in the circuit, so series and parallel connectors in particular. So you take the Kirchhoff domain expressions, which characterize them. For parallel things, voltages are all equal. For series ports, all the currents are equal. You do the same change of variables and get to this scattering matrix formulation. In the same way that you break delay-free loops on the one ports by zeroing out the multiplier, you break delay-free loops that these adapters, they're called, series and parallel signal processing blocks. You break their delay-free loops by zeroing out one element on the diagonal of the matrix. So here we have this this thing on the left with all the gammas. That's the scattering matrix that arises by doing the voltage wave transformation on just saying that the currents are equal. So you have I1 equals I2 equals I3. You do this variable transformation, you get this parameterized scattering matrix. So we can just choose whichever one of the three diagonals we want to zero out, and you just do whatever is necessary to make that happen. So here, the way to solve that 1 minus gamma I equals 0 is to set gamma I equal to 1. And you do that by setting the port resistance for that port equal to the sum of the other two. And if you study electronics, that should look kind of familiar. It's the same as by analogy, it's an impedance matching problem. So you say, what impedance do I see looking into this port? And since it's in series with two other ports, the impedance you see is the other two port resistances in series. And the same thing happens for parallel. So when you look into a parallel port, you see the other two ports in parallel. So the conductances add, or the resistance is the reciprocal of the sum of the reciprocals of the resistances. And you might say, well, can't we have more than three things in series and more than three things in parallel? And what's nice is you can always decompose larger series or parallel connections into a combination of smaller ones. So an n-port series connection is simply n minus 2 3-port series connections put together. And this is really nice because it means we never have to deal with big matrices on circuits that involve only series and parallel connections. We just have these little 3-port things, and we don't have to deal with anything else. The same thing works for parallel connections. An n-port parallel connection is realized with n minus 2 3-port parallel adapters. So to show this basic wave digital filter, linear wave digital filter modeling in action, this is a case study on the TR-808 output filter. So the reference circuit is on the top. This is what's going on the circuit board of this thing. And it's got this nonlinearity, which we linearize in this case. So if you study electronics, that transistor should look familiar to you. It's just an emitter follower, which means that it basically just buffers the two stages of the circuit from one another. Rather than like pulling any funny business and just kind of throwing it away or just decoupling it, though, we actually properly linearize the thing, which gives us a Y-parameter model, which is basically these two reciprocally controlled sources in the bottom. Now the thing has been entirely linearized, and we can transform it into a wave-digital filter. So what we do is we identify all of the pieces that make it up, all the resistors and capacitors, and pull them apart, and we look how they're connected to one another, and separate it out into this rat's nest of individual electronic components, like resistors and capacitors and voltage sources. And the fanciest one is the Y-parameter model, which is the two arrows. I think I have a laser pointer. These two arrows here are these reciprocally controlled, current-controlled current sources. And to make a wave-digital filter out of this, we just transform this scooched around topology into this block diagram. And it should be obvious at a glance that they're isomorphic. There's a one-to-one relationship between each part in the circuit, once you've rearranged it, and each signal processing block in the wave-digital filter. So we showed how to find the representation in terms of adds and multiplies for the resistor. If you want to know how to do all the capacitors and the series and parallel connections and the Y-parameter model, which is a new thing for my dissertation, you should read the literature, because it takes about 80 pages to get through all of them. And it basically all just amounts to you do the same change of variables for every single thing, and you rearrange it to find B as a function of A. So now that that's done, we kind of grab the block diagram and we shake it out into a tree. So we choose this as the root of the tree, we shake it out. So we've got I2 to this inverter, which is the same, this parallel connection, and that's the structure of the computation. So rather than just having a random mess of adds and multiplies that you have to hand code, you can always do a sort of object-oriented arrangement of these things, where you write a little piece of DSP code for this, and it's an object, and it's in a tree structure, so it's a child of this parallel thing, and so on. So ultimately, okay, so here we're testing it against SPICE. Now that it's all set up, we kick a little impulse into it, and we test its frequency response. And SPICE is the simulation program with integrated circuit emphasis, which was made in Berkeley in the 70s. And SPICE is kind of the de facto industry standard for doing circuit simulation, not in real time or with an audio emphasis or anything, but it's a computer-assisted design tool people use to design circuits and verify circuits. So here we kind of use that as an offline, just ground truth to check against. So this is the magnitude response of a family of curves changing the tone and level of the output filter. As you can see, it basically matches everywhere except at high frequencies it falls off a little bit. The issue there is the frequency warping of the bilinear transform. We didn't really go into detail in the capacitor modeling, but capacitors are discretized using the bilinear transform, which is a sort of energy-preserving, order-preserving, conformal map from the S to the Z plane. Basically a way of turning continuous time derivatives into a discrete time approximation on the computer. And the bilinear transform has a well-known frequency warping distortion, which is basically its only issue. And you can see this suffers from that. Luckily it's a low-pass filter, so that you don't hear it, it doesn't cause a problem. If you're giving it the stink eye and it does give you a problem, you just oversample by a factor of 2 and then everything's fine. Actually, if there's anything that can sum up virtual analog in one sentence, it's if you have a problem, just keep oversampling. We run out of computer power though before things get fixed sometimes. So the contributions of this first chapter, all I've really had time to show here is the basics of wave-digital filter modeling and the application of this output filter. But we also worked on parametric wave definition. I show how to model these two-port amplifiers, which haven't been considered in wave-digital filter theory before, but which are important for things like this. And I also use different discretization methods to study the capacitor and inductor modeling, including the warped bilinear transform And this family of transforms called the Mobius transform, which Francois wrote a paper on that I was co-author on last year. I applied it here to wave digital filter modeling and showed that contrary to popular belief, wave digital filters don't intrinsically have to use the trapezoidal rule. They can actually use an incredibly wide range of discretizations. The only restriction, which is another contribution, is that they structurally cannot use explicit discretization methods. So sometimes if you're using forward Euler to discretize a system, you might think that that's a bad idea because it could go unstable. Sometimes it's fine, a lot of times it's not guaranteed to be fine. But actually I show in the dissertation that it's actually structurally impossible to use it in this context. So in the second chapter, we deal with the first of the two main contributions, which is how to handle wave digital filters with complicated topologies. This is something that, I guess because the issue of multiple nonlinearities is so interesting and so important to musicians, and everyone it's kind of a well-known thing that the reason tube amps sound so great is because the triodes are very important. And the reason distortion pedals sound so great is that the specific behavior of the diodes and nonlinearities is important. So because that's such like a hot topic in music and virtual analog, no one really thought about the topologies all that much. The one important previous work is this work by Martens and Meerkotter from 1976. So they work on a global formulation for the entire, scattering matrix for the entire circuit rather than decomposing it. And they built off classical linear graph and electrical network theory, which kind of takes a circuit, turns it into a graph, decomposes the graph into links and twigs, and then does things with that. Linear graphs and electrical networks are really cool, and this is a nice work, but it has some serious limitations. The biggest limitation is that it's limited to circuits where the circuit and cut set matrix are orthogonal to one another. And that's a property which is only satisfied when there aren't any controlled sources or ideal amplifiers in the circuit. And for us in audio modeling, that's a big deal because we often are dealing with controlled sources, often dealing with circuits including op amps or transistors that are working as ideal amplifiers, and none of these circuits are admissible in this framework. So it kind of only works for these very simple rat's nest circuits that don't include any controlled sources or nullers or operational amplifiers or any of these standard audio building blocks. For instance, if we take that bridge T filter, put it in the context of an op amp, so it becomes a bridge T resonator, suddenly it becomes inadmissible, and the method of Martens and Meerkotter won't work. So, should we jump ahead a little bit? What I show in this dissertation is how to use a new technique. I introduced a new technique for handling scattering matrices which can have any of those properties which were inadmissible before. So the circuit can have any topology. It can have absorbed multi-port linear elements or nullers or any of these things, any number of them really, and it still works. So the way this works is by using the modified nodal analysis formulation, which is another like classical circuit formulation that kind of was developed alongside and parallel to linear graphs and electrical networks. So modified nodal analysis relates some current sources and voltage source values to node voltages and branch currents according to some big matrix equation. So my contribution, which basically opens up wave digital filter modeling so that it can be applied to any of the circuits we actually care about, is to confront the modified nodal analysis framework with the very definition of the voltage waves which are used in wave digital filters, do a little bit of matrix algebra, and slam them together into an equation that solves the scattering matrix. And this complements work that was done by Franken, Ox, and Ox to really make all these things possible. So what Franken, Ox, and Ox did was show how you can use graph theory to take a circuit and automatically decompose it into its topologies. And usually with like simple kind of electronics 101 things and little low pass filters and little high pass filters, you can just look at it and be like, these two things are in parallel, these two things are in series. I can just eyeball it and figure it out. But when they include like weird topologies or complicated things, it's not so easy, and you might want to just have a computer do it for you. So they used graph theory to accomplish that, and this data structure for computer science called the SPQR tree. And so they use that to take a circuit, turn it to a graph, do this thing called finding split components, and then that produces a tree structure which is isomorphic to the tree in wave digital filters. And this was a great work, and they really opened up the topological issue, showing what was missing and how you could handle any topology. The only problem is, alongside all this great graph theoretic work and bringing these two fields together, they never actually talk about the signal processing. So this basically lets you draw the block diagram for any linear circuit, no matter how complicated the topology is, and then you're left with something with no signal processing. So you know that there's basically everything complicated is called an R-type adapter, this R. So that's a third kind of thing in addition to series and parallel connections. Actually, R-type adapters are maybe a third class of connections, because it's actually an infinitely large class of types of connections. There's not one R-type connection, there's an infinite number of them. But they never showed what to do with that block in your block diagram. So when things come in, what things come out. And that was my contribution, to say, well, when things come in, what other things come out? And that's what the modified nodal analysis insight handles. So to show that in action, let's look back at this bridge T resonator, which couldn't be handled with the method of Martins and Meerkotter. So, and I should mention that when you see an op-amp in a circuit, that's an electrical device. They're very complicated, made of dozens of transistors and other elements. Usually in circuit design and modeling, we do something to, we have to say what's going on in there. And you can either replace it with dozens of transistors, which would make the simulation incredibly complicated, or you replace it with some sort of simplified model. So the sort of back of the envelope calculations you do in Circuits 101, those are actually what's called a nullor. So the nullor is like a theoretical circuit element, these two little ovally things. It's like the circuit theoretic way of representing those back of the envelope calculations you do in Circuits 101. So saying that no current comes into the inverting or non-inverting nodes of the op-amp, and any amount of current can be sourced, and then the output floats to any voltage it needs to accomplish that. That's like what you say, and then you write out your equations and you move them around and stuff. But in circuit theory, you represent that with this thing called a nullor. And the other way is to use macro models, which are combining controlled sources and resistors. And that's all shown in some of the papers that I wrote. But here we'll just look at the nullor. So first we smoosh it around and uncover this topology. And indeed, the topology has this nullor absorbed inside of it. So what we do is we set up these Thevenin equivalents on each port, which are the hook into the modified nodal analysis domain. And what's nice about modified nodal analysis, I said that this matrix explains how to get from node voltages and branch currents into current and voltage source values. But like, what's really nice is that matrix just, it's completely systematic how to derive it. Even in, it's called stamps. So it's really just a turn the crank operation. You have these kind of templates or stamps of how each element contributes to the matrix, and it's even just automated. But here, to go through it step by step. For instance, we consider this resistor, and we look at a resistor stamp, and it says, okay, a resistor is a thing with a conductance 1 over G going from node I to node J. Okay, so that's node 6 and node 2 for us. And then what it does is it stamps that conductance G into these 4 matrix entries, II, IJ, JI, and JJ. Okay, so we stamp those in. And you can see this same template kind of at play for the other resistors. There's all these kind of like corners of rectangles, sort of templates all over this thing. And for voltage sources, it's the same kind of idea. So voltage source goes from node I to node J, you get 1 at node I, and a new column, and at J, new column, you get a -1. And all these stamps do are, they're just a formalized way of embodying Kirchhoff's voltage and current laws. So the easiest one to see is what's going on with the voltage sources. So if we kind of visually multiply this vector over onto this matrix, this line of the equation right here, all it's saying is that V5 minus V0 equals EA. So that's just saying what the voltage source does. The voltage source is enforcing a voltage EA between those two nodes. And you could derive all this by inspection and by like looking at this and like writing out Kirchhoff's voltage laws and trying to arrange them into a matrix expression. But that's very tedious when the matrices are larger than 3 or 4. So when it has hundreds or dozens of entries, you just want to use these stamps to plug and chug and fill out these matrices automatically. And that modified nodal analysis formulation is due to Ho and Roelli. And then finally, the null OR works in a modified nodal analysis framework by stamping into this column. And all this says is that there's some current, J norreader, that flows out of this node into this node. And we don't impose any other restrictions on it, we just say that it exists. And down here, this last node is kind of like a voltage source. It says that there's the voltage at node 2 and the voltage at node 4 are equal to one another. But we haven't allowed any current to flow, so that indeed embodies the norreader's job to say that no voltage develops and no current flows. So we set all these things up, we plug it into that matrix equation that we developed, and now we have a scattering matrix. We can plug it into our block diagram so that we now have something in that tree structure, and now it works. So by plugging in different values for different drum machine circuits, we can get all these different families of curves. And I don't have a sound of this because it sounds awful. So I don't know if you're used, for people who are used to looking at magnitude of responses, this bass drum, I don't know, I should have calculated the Q, but the Q of that bass drum is probably like 0. It's just like this really flat bandpass filter. If you kick an impulse into that, it's going to resonate for all of like 1/10 of a millisecond. So indeed, it's going to work as a filter. But if you're trying to make a drum sound that like resonates for 1/4 of a second or 2 seconds, this won't do it. So we need to add more things. You know, even though this is the heart of the drum machine and the central concept that makes it work, this resonator, it's not enough. We need to add in all the other things that make it work. Otherwise, you get something that sounds awful. Actually, some old drum machines use kind of this concept, and I'd argue that that's why the 808 sounds awesome, has been used in more records than any other drum machine, and people have basically forgotten about things like the Wurlitzer Sideman and these other drum machines, which basically sound like old-timey, just like automatic cha-cha boxes, but don't have any oomph to them. So in this chapter, the main contribution of the dissertation is showing how to apply modified nodal analysis and confront it with a wave digital filter formalism to handle any topology, which can include all the things that we care about audio, which show up in every single circuit we care about. The null ORs and op-amp modeling, transformers and controlled sources. And as an example, we looked at the simplified version of the bridge T resonator. So now we move on to some of the other auxiliary parts of the drum machine before showing the full nonlinear thing in its glory. This chapter deals with wave digital filters with one nonlinearity. It's basically a review of the literature, but it sets up the next discussion. So wave digital filters have been able to handle up to one nonlinear device since 1989, when Meerkotter and Schultz showed how to deal with an ideal diode or a piecewise linear diode. It basically works by taking this piecewise linear representation, doing a variable transformation on it, and then wherever you are in this curve, it's acting linear at that point, so it can be solved. Since then, there's been a long history of increasingly refined models of handling single nonlinearities. Julius and David Yeh worked on just writing out the entire nonlinear equation and solving it iteratively. Rafael Paiva et al. Worked on using the Lambert W function to explicitly solve the Shockley ideal diode law. I worked, one of the contributions to this chapter that I worked on with Vaibhav, Nangia, Alberto Bernardini, and then our collaborators in Italy, Alberto Bernardini and Augusto Sardi. We worked on a more complex model which uses a second Lambert W evaluation to refine that approximation. We also generalized it to any number of diodes. Any number of diodes going in one direction and any number of diodes going in the other direction. That's something that's very common in audio and distortion circuits. You'll have what's called a diode clipper with one facing up, one facing down, or any number facing up and any number facing down. So we kind of generalized and improved that. Finally, another contribution is that Julius and I worked on energetic interpretations of any of the errors of these methods. So figuring out, if you make a simplification, will it cause the simulation to blow up, or will it cause it to maybe be slightly damped, but generally okay? We won't go into those further, but you can check the references if you want to know exactly all the details. Here I'll just show it in action on the pulse shaper. So here we use the Paiva model, which is to explicitly, so this is the Shock-Ideal diode law. It relates the diode's voltage to its current according to this exponential relationship. The IS and VT are thermal and device properties of the diodes. So you kind of you plug in the voltage waves, you get this horrible transcendental equation, which just luckily is in a form that the Lambert W function can solve. It's rearranged here, so when a voltage wave A comes in, it can explicitly be solved for B. So we take the circuit, it's rearranged into a wave digital filter block diagram. So you can see that these two things are in parallel, for instance. So here they are down here, plugged into a parallel adapter. The diode and the resistor 162 are in parallel, so indeed they're plugged into a parallel adapter here. And this gives us a little tree, a bush, I don't know, a small tree structure that we plug the standard building blocks into. So something interesting and unexpected that came up here was that we need to actually think hard of the discretization method for this circuit. When we use the standard bilinear transform from the literature, it doesn't match the SPICE simulation at all. So SPICE is the blue trace here, and our wave digital filters are red trace. It's like nearly complete garbage. It should be letting this big pulse through and then having a tiny pulse going the opposite polarity. But it kind of makes a huge pulse, which looks fine, and then this medium pulse going in the wrong direction. So it's utter trash. It doesn't look in any way like the original, what it should look like. And so what we did was we worked on different ways to discretize the diode. In this case, using backwards Euler or this family of alpha transforms that Francois worked on in his Mobius transform paper fixes the problem. So actually this one value of alpha equals 0.029 minimizes the error, but backwards Euler works all right too. So you can see down here the curves are basically overlapping with one another. So for me, this is kind of a killer app of the Mobius transform, and it's a good example of why a trapezoidal rule isn't always the be-all and end-all, and you may have to break into some other methods to get things to work sometimes. The main contributions of this chapter, which I'll refer you to the papers for that, are the energetic interpretation of the nonlinearities, improving the Lambert W based approximations for the diode clippers, and then finally this application to the next part of the drum machine, which is the pulse shaper. So the last chapter here deals with wave digital filters with multiple nonlinearities. This is kind of like the holy grail of wave digital filter modeling for audio circuits, because audio circuits sound good because of the nonlinearities. At least this is what they say. I agree with they. This is the thing that's received the most attention in the literature. So I'll review some of what's been done in the literature, how people have tried to solve this problem for specific cases before explaining my contribution. So one of the first things that had been done was Matti Karjalainen and Jiri Pakarinen worked on modeling a simple triode amplifier. And they came up with a way of, a triode is this three-terminal device here. It's got a grid terminal, a cathode terminal, and a plate terminal. And they kind of used some, I would say they used domain knowledge about a triode to say, well, even though in theory current can flow in the grid, because of the way it's configured, the grid current's pretty small, it probably doesn't matter. So they just decided to ignore the grid current. And they're left with kind of a one-port device, just it's got a terminal at the plate and a terminal at the cathode. And then they said, okay, the way that one-port device works is parameterized by the voltage at the grid, even though no current can flow in there. Well, you know, that creates this sort of implicit relationship between pieces in the circuit, so it's hard to realize that. So they just throw a delay in and say, well, let's just pretend it was parameterized by the previous value of that voltage. And it worked pretty good, and indeed that works. It works for simple triode amplifiers, and they refined it in a series of 2 more papers. But it's not very generalizable, and it relies on the triode being in this one region of operation, and indeed, guitar aficionados will tell you that the grid current is not 0. It's pretty small, and if you have to throw something away, it's going to be the grid current, but it actually affects the simulation significantly, enough that Ross is nodding his head in disbelief. Related to this is some work done by Alberto Berardini in Milan, and so Alberto kind of generalized this to transistorized and diode circuits, saying, well, depending on the region of operation of the transistor circuits, we can sometimes throw away one of the PN junctions. And it similarly works pretty well, and but only when the transistor is stuck in one region of operation and doesn't move. So for the drum machine, for instance, it wouldn't work so well because these transistors are acting more like switches than amplifiers. They're turning things on and off. They're like opening up the envelope generator or letting it build up and letting it die down. So they don't stay in one region of operation. Another work done in Italy is by Giovanni De Sanctis and Augusto Sardi, and they kind of showed how you can like finagle nonlinearities up to the root of a tree and then let things hang off of it. And this is really philosophically, this is the root of my work, but you can see some problems with it, that the dimensionality of this problem grows without bound as the topology gets complicated, which is a problem because you may have a circuit with, say, a single transistor, but then you could end up with a 10-port nonlinear, or you could end up with 10 coupled nonlinear equations to solve, even though there's only 2 nonlinear devices in the circuit. And the same kind of approach was taken by Stefan Petrosh and Rudy Robinstein in 2004. There's other iterative methods that work to solve these mutual non-breakable dependencies that are set up, but and that's led by Tim Schwertfeger and Anton Kumar and Wuppertal. And the issue with this approach is that it doesn't localize the problem to one part of the tree. So you could end up with a circuit where there's 2 problematic things very far from one another, and the entire circuit has to be iterated to solve this. You can't just localize it. So, to summarize, the problem with existing work is that, and no one of these approaches has all of these problems, but all of the existing approaches have at least one of these problems. They either involve introducing ad hoc delays, which screw up the accuracy of the simulation. They involve simplifications to the nonlinearities, throwing diodes away, assuming grid current's 0, which screws up the simulation. They're limited to certain topologies, which I'd argue is the biggest limitation. The difficult part of the problem isn't necessarily localized to one part of the simulation, and the dimensionality of the nonlinear problem that needs to be solved can just keep growing and growing and growing, even when you aren't adding more nonlinearities to the problem. Just as you add linear components to a circuit, you end up with more and more nonlinear problems to solve, which is a huge bummer, and I think it shouldn't be like that. So, what we want is something that doesn't have any of these problems. We want no ad hoc delays, no simplifications to the nonlinearities, something that works for every topology, localizes the difficulties to one part of the simulation, and lets everything else work easily and effectively, and doesn't grow the dimensionality of the problem any larger than the number of nonlinearities at the most. So the way we do that is we apply the graph techniques of Franken-Ox and Ox to smoosh things right into a block diagram that localizes all the nonlinearities to the root of the tree. Then we we have this rat's nest of wires that connects the nonlinearities to the rest of the circuit, which we solve using the scattering matrix formulation from chapter 2. And the combination of that vector of nonlinearities and the rat's nest of wires that connects it to the rest of the circuit is solved using Newton's method or using table lookup. Table lookup is very standard in audio, but it gets kind of hard when you get maybe above 2 or 3 dimensions. So Newton's method steps in at that point. And this will work for any circuit. It doesn't require any simplifications. So what it looks like in sort of a matrix vector form is you have all this stuff happening below. That's all your normal wave digital filter trees. Then you have this rat's nest of connections, which gets represented by a scattering matrix, S. You have this transformation of variables to get you back to the Kirchhoff variables that characterize nonlinearities. And then you have the vector of nonlinearities themselves. This thing is riddled with delay-free loops. So we first resolve some of them using algebra. And we're still left with this one non-commutable loop at the top. And one way to resolve this is by shearing, it's kind of pre-solving it with the table. And you can use scattered interpolation or structured interpolation to look up a solution to that. Another even arguably better way to solve that is to use Newton iteration. And so for more details on that, I refer to a paper by Michael Olson, who really dug into that in this context and looks at some of the situations when it works and doesn't work, and how to make some decisions and how to get an improved initial guess. But some combination of table lookup and Newton iteration will solve that. And so what's great about this is that it takes something that required ad hoc approaches and pretty deep domain knowledge about how circuits work, and for this triode, is the grid current important or not? And it turns it systematically into a standard engineering problem. Anyone who's done any form of engineering has used a Newton solver to solve a nonlinear equation, and there's a bit of an art to it, and there's some parameters to tweak and some choices to make about initial guess and all that. But it's a standard off-the-shelf engineering problem rather than something that needs deep circuit voodoo knowledge to figure out how to turn it into something manageable. So to show this in action, we've got the envelope generator from the TR-808 and also the full-on nonlinear bridge T resonator. So we break it up. As I said, we gather all the nonlinearities together at the top of the circuit, and then there's this rat's nest of not quite series, not quite parallel, just a bunch of nodes and wires and a tangle of things connecting it to the rest of the circuit. And we look at that rat's nest and find its scattering matrix using the techniques of chapter 2. And we get this sort of tree structure like this. So we have all the nonlinearities up top and the rat's nest scattering matrix. And those two things are jointly solved using Newton's method.
Does R stand for rat?
R node.
Technically, in the literature, R stands for rigid to some graph theorists and strongly connected for other graph theorists. I'm serious. Although I propose that Doug's idea that R stands for rat's nest be adopted in the digital filter context. So those are resolved with Newton's method, and everything else that hangs off of this is handled with standard 1970s wave digital filter techniques. So all this stuff and the rest of the circuit.
Vintage technique.
Vintage wave digital filter techniques. Yeah, I'm sure there'll be a Karma dissertation like 2050 that's about like the failings of wave digital filters and why those failings sound super awesome and trying to emulate them.
Bring back the binary transform loss. Right?
Yeah, it's like, oh yeah, the new stuff is so good, but that standard the bilinear transform, frequency warping is just so warm. You heard it here first. So this is a pretty boring circuit. You just kick a little impulse into it, the dotted line, which is 1 millisecond wide, and then it produces this envelope. And indeed, for various sizes of the input pulse, it does match SPICE. So it works. Again, this wouldn't sound like anything except like a thunk. It's just kind of like a 5 millisecond wide thing. But the shape is very, I'd say, non-parametric, and we don't really have to think about how it works or why it works. We just plug all the circuit stuff into the simulation, turn the crank, and it's done. It's because it's not a standard attack release decay sustained sort of envelope. It's just these transistors and these things connected together.
Is that little gap at the beginning, like for 4 volts immaterial, or?
That gap is, I wouldn't say immaterial, but it's not that important. The effect of the envelope generator is that during these 5 milliseconds, it kind of switches this transistor off downstream, which changes the frequency. So yeah, if you have a kick drum and you like step on the beater, there's a moment when the beater is like in contact with the drum. And during that moment, if you're putting tension on it, the drum's resonant frequency rises. Or you could say another effect is while the beater is touching the drum head, the 1-1 mode of the drum, just like the normal in and out mode of the drum, is damped. So it can't vibrate because something's pushing on it. So the Roland engineers who designed this thing in 1980 were smart people, and they recognized that, and that's why their kick drum is being rapped about 40 years later, and nobody's rapping about the Wurlitzer Sideman, because they recognized that thing and designed this envelope generator to imitate that effect in a sine wave. Actually, there's who wrote it? There's an Acoustical Society of America article about using sinusoidal modeling to mimic kick drums, and I think this is from like the 60s and 70s. They got good results with like 500 sinusoids. The Roland engineers got good results with 1 sinusoid. They just tweak its frequency and do some transient things. So these are smart people, and I think in addition to just sounding awesome, I think their smarts are part of why they think people still talk about this drum machine. They might not know that's why, but I think it's why. So finally, the piece de resistance is the full nonlinear bridge T resonator. This thing's kind of complicated and a pain to work with because it has these 2 infinite resistance Nuller amplifiers built into op amps. It has a transistor, it has a diode, it has this complex topology, bridge T topology here, which is a pain on its own, mixed with the feedback path. So it's a mess to try to model this with standard techniques. If you want to see what that mess looks like, you can read one of my papers from 4 years ago when I tried before getting into this and solving any problems just using ad hoc techniques. Here though, we turn the crank using the techniques we derived earlier in this chapter and the second one. We figure out the topology, we use math to find the scattering matrix of that thing, we shake it out into a tree, turn it on its side because it didn't fit right. We resolve the nonlinearities and Ratzen's number 1 with Newton's method and everything else using standard techniques, and then it works. So it's almost indistinguishable from SPICE, just matches up perfectly. And at this point, after showing you a lot of math and figures and talking about graph theory and links and twigs and voltage waves, finally I have some sound to play for you, which isn't just little clicks or little control voltages passing through that don't sound like anything. This is the real deal. So, that was it working. Yeah, so the main contribution before the sound, the main contribution of that chapter is this utterly general technique for handling any number of nonlinearities confronted with any topology, which gives us a systematic way of just taking any circuit, turning it into a wave-digit filter block diagram, resolving the EVZ parts using 1970s techniques, and then resolving the hard parts with off-the-shelf engineering Newton solvers. So finally, let's look at a couple different families of sounds that can be produced with this and show that the wave digital filter matches SPICE. All right. So here is changing the amplitude. So first, soft amplitude, and we get louder and louder and louder. In each case, I'll play the ground truth first, and then the wave digital filter simulation. Let's hope they usually sound the same. So what's interesting about the amplitude of this is that when you're changing the amplitude of the drum, you don't just change how loud it is, you also change the timbre, which is something kind of hard to parameterize or explain exactly, but which we get for free in the physical model. We don't actually have to understand it to make a good model of it or to make it work, but we can remark about it a little bit because it's interesting. So you can see here that depending on which curve you're on, like fading from blue to red or from like low voltage to high voltage, the transient at the beginning versus, it's split into two phases. Either the transient is loud or the remainder is loud. So when it's quiet, the transient doesn't dominate the signal very much, but the resonance dominates when it's quiet, and the transient dominates when it's loud. So there's also a timbral shift as you're changing the amplitude. At the same time, you can see that these waves go out of phase a couple milliseconds in, and that's because the pitch is also affected. So the envelope, because of what's happening in the envelope generator, and because of what's happening with this, because the amplitude feeds back through the circuit to change the pitch based on the amplitude, louder things also cause like a bigger pitch glide. So there's a lot of interesting timbral things going on, and I'm kind of limited in my ability to explain it, but the good thing is that with wave digital filters and physical modeling, you don't have to be able to explain it. You don't need any deep knowledge of why these circuits work or what's going on. You just need to plug and chug. So here's showing the tonal capabilities of the drum. First, tone knob all the way up, and then family of curves going to quieter and quieter. Again, first spice, then the wave digital filter. So that's one other dimension of tonal control available on this drum machine. Finally, and this is kind of maybe the most exciting one, is the decay knob. So I think that actually the shortest decay time sounds like garbage, but then everything from the middle to the top are these classic sounds that you've heard in rap music and EDM and pop music probably 10,000 times, kind of on the spectrum from like Marvin Gaye to like Beastie Boys. So first the short one, and then Marvin Gaye, and then Beastie Boys. Yeah, 20% is when I think it starts getting interesting. That's maybe past Beastie Boys into like rap bassline territory. And finally, this is something interesting you get for free from the simulation. Part of the discourse around old electronic musical instruments is that they kind of breathe or have some randomness to them, and there's variation from unit to unit. And it's something you could kind of mimic with a black box model. You could say, okay, well, if every hit of the drum is a little random, we add some white noise, we randomize some things. There's a lot of music products have like a humanized function in them that just like screws everything up a little bit. And it's like, because humans are terrible at everything, so we'll just make this a little terrible. What's nice about physical modeling is that you get this sort of stuff for free. So this variation in amplitudes of the drum doesn't come from introducing randomness or fuzzing the parameters or humanizing it or anything. It comes from, it's kind of the you and your buddy jumping on the trampoline effect. This is an electronic circuit with like signal bouncing around in a resonator, and depending on where it is in the resonator as it dies down, the next note's going to be louder or softer. You know, if you both jump at the same time on the trampoline, one of you's going flying. If you're on the way down and your friend's on the way up, you're both going to kind of fall, and it's going to be a weird thing. And you know, that's not like your ideal acrobatic moment. And this is the same thing, and we don't have to humanize the simulation or add randomness. It just happens for free. So you can I'll play 8 seconds of this, and you'll hear that there's some variation built into the simulation. So finally, to conclude, before there were all these things wave digital filters could do, and then all these very important things which are crucial for audio modeling they couldn't do. And what we've done is just fix that, so all the things they couldn't do, they now can do. And most notably, complex topologies and multiple nonlinearities, and ad hoc things that require lots of smarts being turned into systematic standard engineering problems. And beyond just the drum machine, which is my favorite, this has also enabled all kinds of other simulations we've done, written some papers on. We worked on the tone stack, the Ibanez tube screamer, the Big Muff Pi distortion pedal, the Ibanez tube screamer tone stage, some more complicated op-amp macro modeling, the Hammond organ vibrato chorus circuit. Mike Olson worked on common emitter amplifiers. Ross did what is still the largest wave digital filter simulation I know about. It was the basement preamp, which he won one of the best paper awards for at DAFX this year. And Max Rest worked on the common cathode amp using some of these techniques. And this, you probably don't have time to read this, but for people with slides, this is the list of references of some of the papers we wrote and related work. So yeah, finally to conclude, I just want to thank everybody who's helped me with this research. I feel like there's this aphorism floating around CCRMA that a dissertation is primarily a solo endeavor, and I respectfully have to disagree, because I definitely couldn't have done any of the work I did here, or gotten into this, or had the freedom to work on what I wanted to work on without the support of everyone at CCRMA. And this should be a much longer list, but I just want to point out a few people who were especially important to me. Francois has been with me since the beginning. We're a PhD class together, and more than anybody, Francois helped me do my best work and was never let it be good enough in the best and most helpful possible way. And the most rigorous and best part of the stuff I've done always bears some mark of Francois's always helpful criticism. Vaibhav spent time with me at the beginning when I didn't know what a wave digital filter was, and we spent a lot of time at Coho drinking coffee and trying to figure out what in the world was going on in the papers from the 70s, which are kind of written for German radio electronics engineer audience, and as non-German, non-radio engineers, we had it's kind of hard to get into them. So Vaibhav spent some real time in the trenches with me on that. The last year and a half, Mike Olson, Ross Dunkel, Max Rast, and Albert has spent a lot of time with me and helped me take this stuff to the next level. And we had like a great group working here, and I think we got a lot of cool stuff done. And especially Mike's work on the Newton solver really helped to take things to the next level. In Milan, Alberto Bernardini and Augusto Sarti have been really important collaborators for the last 2 years, and we've written quite a few papers together, and they're very hospitable in our visits over there. And so I really want to thank them, and I hope we get to continue working together in the future. Some of this stuff is kind of aiming towards journal articles, and we'll work on those together. Chet was always a ton of fun, and we got to work on a paper together, which was great. The Ibanez Weeping Demon pedal, probably like a not very famous, kind of trashy, horrible wah pedal, which was its own unique sound. And Manik Sanguinaria, who we came in the first time, and we wrote some of our early papers together, which aren't really on this topic, but were kind of fun too, on granular synthesis and some digital circuit bending modeling. I want to mention some people at CCRMA who just completely stepped out of their way to help me over the years. People really didn't have to, or could have just let me do my own thing, but went out of their way to make sure I was doing okay, and yeah, really give me some great opportunities. And I want to mention Dave Kerr and Carl Wilkerson, Fernando, Jorge Herrera, Dave Berners, Owen, Chris Jetty, and Greg Kovacs, who's not from CCRMA, but from the Transducers Lab in Double E, who let me do some work there and gave me a desk in an era before when CCRMA had desks for grad students. And Nettie and Debbie. Finally, I want to thank I want to thank my committee, my advisor, Julia Smith, Jonathan Abel, Jonathan Berger, Chris Chafe, and Doug James, who's chairing the session, who have just been completely inspiring and completely pushed me in all the right moments and completely left me alone in all the right moments and gave me all sorts of great opportunities and always supported me no matter what sort of weird math thing I was working on, whether or not they actually care for booty-based drum machine sounds or not. So and thanks for putting up with that. Hopefully, you guys can take that back and do guitar stuff actually with the research. Finally, I want to thank my parents, Craig and Kim Werner, who also, I think, pushed me when I needed to be pushed to do things and left me alone to do whatever weird thing I was doing when the time was right. and my partner Melissa Kagan, who I think nobody in the world cares less about wave digital filters, but spent so much time hearing about wave digital filters. And for that reason, I don't think anyone has suffered more than her through this dissertation. If you think that you're uninterested in hearing about arbitrary invertible scattering matrix formulations, you can know that Melissa isn't, but that she was much more of a trooper than you were in hearing about it. And then, I mean, it's impossible to thank everybody, but, you know, just here's everyone else for posterity. So thanks, and I look forward to entertaining some questions if you have any.
First off, great job, that was awesome. My question, in the first chapter, when you shake out that circuit and turn it into a tree, you pick that current source to be the root node. Did you have to do that?
That's a good question. And so this is related to the fact that wave digital filters can only accommodate, could only accommodate one nonlinearity in the past. A kind of broader way of saying that is that they can only accommodate a single non-adaptable circuit element. So nonlinearities are non-adaptable because their operating point changes depending on the voltage or the current, whatever your pleasure is. But there's also linear devices which are not adaptable. So ideal voltage sources, ideal current sources, short circuits, and open circuits are all non-adaptable. So if you're lucky and you have a circuit with a single non-adaptable element, you just put that at the root. If there's nothing in the circuit which isn't adaptable, if it's a linear circuit and all of the sources are non-ideal and there's no open circuits that you want to expose to look at their voltages, then it's nearly completely arbitrary what you pick. Actually, you know, in the old school literature, they had a sort of numerical reason for picking one over the other that had to do with the dynamic range of the mathematics. Probably with IEEE floating point numbers, we don't care about that anymore. But they would choose whichever element as the root that would minimize like, the variation in port resistance values or something. Nowadays, I've never experienced any discernible issue. So yeah, if you have one non-adaptable element, you pick it as the root, whether it's linear or non-linear. If you have two, you either use techniques from my thesis to handle it, or often, if those things are linear, you can just throw a nonsense element in to fix it. So if you throw a 1 ohm resistor in source with a voltage source to turn an ideal source into a real source, you know, the wires in the circuit probably have 1 ohm of resistance, so it's no big deal. Likewise with current sources, if you throw a 10 mega ohm resistor in parallel with the current source, it's not going to cause any problems. Likewise, if you replace a short circuit with a 1 ohm resistor or an open circuit with a 100 mega ohm resistor, it's really not that big of a difference because like between two nodes on a circuit board, there's probably 100 mega ohms of resistance. They're not truly isolated from one another. So those techniques, when things are all linear, I talk about it in my dissertation and like drill down into that, explain all the cases, and even introduce a technique which I didn't talk about for resolving multiple linear non-adaptable elements when you don't want to make those simplifications. But for the linear ones, people usually just throw in a tiny or gigantic resistance, as the case may be, to sidestep the problem.
Thank you.
Can you repeat the questions for the stream then they can?
Oh, sure, yeah. So retroactively, Chet was asking why I chose the ideal current source as the root of the tree for the first chapter case study. Ross?
So I think it was the pulse shaper circuit where you had the sort of dramatic failing of the bilinear transform.
Yeah.
I was just wondering if you could talk about that a little bit more, and if you had any kind of insight into why that happened, what the value of alpha that you ended up with, what does that mean? Like what just curious about that.
Thanks. Yeah, that's a good question. So Ross was asking about the Chapter 3 simulation, which dealt with the pulse shaper and why, what's going on with that dramatic failing of the bilinear transform, and can I comment on the alpha the value of alpha that worked the best. So it's a very good question, and I have some insight about why it didn't work and why the value of alpha we chose does work. So for the first part, the reason the bilinear transform doesn't work is because the instantaneous poles of the system. Okay, so let's back up to the diode shaper circuit. Basically, if this node voltage here is low, if it's below 0 by much, it reverse biases the diode, and the diode only lets nano amps of current through it. It might as well not be there. But then, if this goes much above 0, the diode starts to conduct like crazy. So usually when we talk about that, we kind of just think in the time domain, and we're like, oh, the diode limits the voltage excursion. But if you think about the poles and zeros of the system, what's happening, limiting the voltage excursion, is equivalent to damping the poles of the system, like on the S-plane out to like infinity. Like if it completely brick wall limited the voltage excursion, and you also drew out the poles and zeros of the system, you would see that they get slammed out towards infinity. So on the Z-plane, poles being slammed towards infinity is equivalent to poles all clumping up at Nyquist. So what you get is this, it sets off this like transient ringing at Nyquist. And that, you'll see that in distortion circuits, not hear it, but you'll see it, and it's not that big of a deal. But in this circuit, because it's like the diode is actually turning on and off, once it starts this really fast Nyquist ringing, like it basically switches every single sample, one sample later, it disengages and then goes back to just pretending the diode isn't there. So, basically you damp the poles out to infinity, it becomes an incredibly overdamped system, starts to ring, and once it starts to ring, the nonlinearity which caused that ringing immediately disengages, and then the state decays. So, it's something that like the drum machine circuit really exposes as a problem when you wouldn't necessarily have to think about it that much on distortion circuit. To answer the second part of your question, why that value of alpha? In this case, what I did was try backward Euler. I found it worked and said great. And then I said, well, let's try these alpha transforms. And I chose the one which minimized the RMSE. But to talk more about why that alpha value might be the one that minimizes the RMSE, I direct you to part of the paper Francois wrote that I co-authored with him on the Mobius transform. There we kind of looked a little bit at this one. We looked at how the poles move around as nonlinearities engage and disengage, and tried to come up with this criteria that like ensures this damping monotonicity. So if the poles are going to go towards Nyquist, at least an increase in S-plane damping should lead to an increase in Z-plane damping, and there shouldn't be any inflection. So we have some kind of anecdotal evidence that, well, no, there's a rigid mathematical proof that as S-plane poles go from the J omega axis over, you come off the unit circle on the Z-plane, kind of glance past the origin, and then end up at Nyquist. This is because conformal maps preserve right angles. So once you kind of glance past the unit, or glance past the origin, you're in this weird situation where although the continuous time system is having increased and increased damping, the damping on the discrete time system is actually decreasing. Like as that pole moves like away from the origin towards Nyquist, the damping is decreasing. It's turning back into an oscillator if it ever actually reached. If it ever actually made it to the unit circle, it would become an oscillator. And it is indeed asymptotically approaching the unit circle at Nyquist. So like that moment where it glances away and increased damping starts to cause decreased damping is like total bad news, anecdotally. It's just, it doesn't make any sense that decreased damping should translate to increased damping. So Francois and I tried to design our transforms to ensure that no matter where the poles are, they're always in the monotonic region at the very least. And that could be a way to choose the value of alpha for the Mobius transform so that it works. That could be, we have anecdotal evidence that that's a good criteria to use. we should have working on a diode clipper, which was used in kind of distortion mode, like in the context of guitar distortion, and yeah, in that labor. Done.
Can you comment on the computational complexity of this method for circuits? It seems like a lot of the key circuits are not necessarily, they're great not because they're complex or huge, they're very specific structures. Is it the case that this method is sufficient for pretty much any of the circuits you want to consider, or are there some that are just really complicated and scalability is an issue, or is that not the case here?
Let me move to a diagram. Okay, so Doug was asking if I could comment on the scalability of this and the computational complexity, and if it's the case that there are some circuits that are so big that they can't be handled. This last circuit, the nonlinear bridge T resonator, you can see the scattering matrix which interfaces the vector of nonlinearities to the rest of the circuit is so big that it almost eats up the entire circuit. There's only this little nub of a tree, this little twig that actually hangs off. Like the tree structure is it's dominated by just that one central scattering matrix. So I would say in the case of this particular circuit, you aren't able to make all that much advantage of the classical wave digital filter results, which let you, whenever you can shear things off into these trees, they're order preserving, they have these guaranteed numerical and energetic properties. They're just like, it's really fantastic. So in the case where it was so complex that it ate up the entire circuit, and there was literally no identifiable circuit components which are in series with one another or in parallel with one another, then I think it would basically become identical to the standard state space formulation, only with a different set of variables. It would become state space in the wave domain, like one global state transition matrix, one global input matrix, one global output matrix, just with wave variables instead of Kirchhoff variables.
The cost wouldn't be linear in the number of states, though.
And yeah, that getting at the second part of your question, in wave digital filters, the cost, in standard wave digital filters, the cost is kind of linear as the complexity of the circuit grows. So as you add a resistor, you're usually adding like one adapter and one multiplier. If you're adding a capacitor, you're adding one state and one multiplier, or one adapter to mush it into something. But then as you get these complex topologies, it's still linear with the number of elements, but like the linear cost of an R-type adapter is large. It's still n times the number of R-type adapters, but n is tiny for a parallel adapter and large for an R-type adapter. This is, I think, a broader implication of my dissertation is how to reconcile state space and wave digital filter approaches. I mean, really what I'm doing at the root can be considered just state space for the part of the circuit which is best handled with state space, and classical wave digital filters for the part which is best handled with classical wave digital filter approach. And we haven't actually studied where the line is to go full on state space or full on wave digital filters. Well, we haven't formally studied the line between my technique, which is kind of a compromise, and full on state space. But I can say that in state space, the complexity grows quadratically with the number of states. So if you have 10 states, your state transition matrix is 10 by 10, because you have to know how do those 10 states influence the time evolution of those 10 states. So it's weird. Like in state space, you could add 10,000 resistors to a circuit, and you wouldn't increase the computational complexity. But you add 2 capacitors, and you add 2 to both dimensions of a matrix multiply. So it depends. The place where the line is for computational complexity depends on how many of the circuit elements are reactive versus how many are algebraic. And it also depends on whether or not the topology is tractable. I think, and this is anecdotally, I think if the topology is entirely one rat's nest with no identifiable series of parallel connections, it's a complete toss-up and they're identical. And I think if you can start shearing things off, then it's good to use this compromise in my approach. But if it literally ate up the entire thing, and you were more comfortable with the state space, then I think that they'd be equivalent. You should just go with whatever you like.
How do you resolve the delay-free loops in the state space case?
Julius asked how to resolve the delay-free loops in the state space case, and in state space, delay-free loops are resolved in exactly the same way as what I'm doing. I mean, what my contribution was to show how to formulate the vector of nonlinearities and the rat's nest that connects it to the classical wave digital filters as a state space system. So it's formulated a little bit different because the reactances merge their way into the equations, but you basically resolve the delay-free loop with Newton's solver, or you resolve it with table lookup. There are even these kind of exotic techniques for doing that with like nonlinear kernel regressions or like genetic algorithms. Like it's like a standard weird engineering problem. So any sort of crazy thing people do, whatever their pet project is, can be used. But like I would say it's like Newton's solver is the most important, then tables, then like kernel regression and Volterra stuff, and then all the weird stuff. Dave?
Max and Chris are watching in Berlin, and they're asking, Max asked the question, how is the wave digital filter 808 kit implemented, and does the model run in real time?
Model does not run in real time at all. And the reason for that is because it's implemented using a MATLAB library, which is made for research purposes. So it's appropriate Max asked this question, because Max Rest came here for a visiting scholar jaunt last year and worked on a lot of papers with Ross and Mike and I. And he, along with Ross, they wrote, Mike and I helped too a little bit, but they wrote a real-time C++ library to implement my research from the previous year, and Max earned his master's thesis based on that work. So MATLAB is garbage for this computationally. The reason being that, as I said, this beautiful object-oriented tree that lets you just write a little library and simulate an entire circuit with like 200 keystrokes only is just trash in MATLAB, because when you pass objects between MATLAB, it kind of like copies the entire data structure and builds a new one just to pass it, and it's just trash. So this doesn't run in real time at all. I think Max showed that for circuits, modestly sized circuits with like 3 nonlinearities, just doing it in C++ like speeds it up by factors of like 10,000. So it's anecdotally, the ones that I hard coded, which weren't part of this presentation because they weren't the drum machine circuits, the Hammond organ vibrato chorus, which is like this giant thing with 36 states. I wrote that in C++ and it runs as a plugin using 1% of the computer's resources. It's less computationally expensive than the sine wave generators that I use to make the Hammond organ sound. So wave digital filters have very nice computational costs, which are not, which the MATLAB research tool does not do justice to at all.
Are there any other questions? Okay, if not, I think we'll thank our speaker.